Through the eyes of Outer Wild Venture's newest recruit, we explore the solar system and unravel its mysteries. We find that a significant portion of the solar system have areas, or even celestial objects, governed by quantum mechanics. We also come across the Nomai, a highly intelligent ancient race who mapped out and utilized many of these phenomena. But they made a mistake, and it's actually quite a common one. The quantum phenomenon we're going to look at is the behavior of the quantum shards. The Nomai found an interesting rock in one of the caves of Ember Twin. The rock comes and goes when no one is looking. One of the Nomai accidentally found out that if they were standing on it and turned the lights off, they could travel with it to a new location. Once our Outer Wilds Venture explorer makes the same discovery, they find Nomai writing in one of the locations to which the quantum rock travels. In this text, the Nomai theorize about the phenomenon they've just experienced. It reads, "We theorize, when a conscious being is in contact with a quantum object and ceases to act as an observer, explaining the need for darkness, the being can become entangled with the quantum object and they move together." Now, quantum entanglement is a real thing, and it is wild, but this analysis is going to focus on the observer part. If you're not familiar with quantum physics, this whole concept might seem utterly ridiculous. An object moving around only when it's not observed. Well, it is very much a real thing. It's called the Quantum Zeno Effect, a feature of quantum mechanical systems that can prevent them from changing while being observed. And this effect has in fact been experimentally verified. In 2015, at the Cornell University, they were able to conclude that the atoms in their measurement setup would not move while they were being observed. So, by continuously observing these atoms, they were able to more or less completely freeze them in place. When they were no longer observed, they would escape their containment through quantum tunneling. And this is probably what we're seeing in the caves of Ember Twin. Quantum tunneling allows objects governed by quantum mechanics to cross energy barriers that they should not have enough energy to cross, according to classical mechanics, thus allowing them to appear in locations that classical mechanics would not allow. For example, if you were to manually throw a tennis ball at a brick wall, it would not have enough energy to penetrate the wall. But if the ball was governed by quantum mechanics, there would be a certain probability that it would end up on the other side of the wall anyway. Okay, so what's wrong with the Nomai's theory? They assumed that the observer had to be a conscious being. This is not the case. That is not the reason it needs to be dark for the quantum rock to move. But interestingly enough, this particular misconception just so happens to be prevalent here on Earth as well. I'm going to theorize a bit on why this misconception is so common. Given the, for humans, incomprehensible behavior of quantum systems, it is certainly not hard to understand why you would make this assumption in the first place. When you're looking at a quantum system, it behaves a certain way. When you're not looking, it behaves in a different way. The pioneers in the field of quantum mechanics realized early that consciousness did not play a part in the behavior of quantum systems and tried to shoot down any incorrect claims, in favor of what is usually referred to as the Copenhagen Interpretation. With limited success apparently, since theories about the conscious observer persisted. The introduction of quantum mechanics into the world of science caused dissonance in the scientific community. Several prominent physicists of the time did not agree with the Copenhagen Interpretation. This dissonance allowed for philosophical interpretations to manifest, which couldn't really be contradicted by a unified science force. And the reason these philosophical interpretations of the observer has lived on might be because it is really hard to grasp the concept of observation in this context. I have not found any one source that could explain this concept in a satisfactory way. It seems like one of those concepts you will have to approach through accumulative research. Regardless, I will share with you what I have found. We're going to start by separating observations in classical mechanics and observations in quantum mechanics. And to do so, we're going back to the beginning with Paul Dirac's The Principles of Quantum Mechanics from 1930, where he discusses the limits of observation. Let's start with an example of observation in classical mechanics. Let's say you want to know the temperature of the marshmallow you're roasting. You put in a good old-fashioned food thermometer as it is roasting, but your oven window is too dirty for you to see what the thermometer says, so you have to open the oven hatch to look. The heat escapes from the oven and you have significantly affected your measurement object, the marshmallow, to get the measurement. So, to improve the measurement setup, you go high-tech and buy one of these fancy wireless food thermometers. Now you can view the temperature reading from outside the oven, and it has practically no impact on the result. So by improving the measurement setup, you have practically eliminated the interference of the measurement. The observation of what temperature the marshmallow has does not affect the temperature of the marshmallow. So, in classical mechanics, it is theoretically possible to make an observation that does not affect the system. This is not possible in quantum mechanics. Dirac writes, "In order to give an absolute meaning to size, such as is required for any theory of the ultimate structure of matter, we have to assume that there is a limit to the fineness of our powers of observation and the smallness of the accompanying disturbance. A limit which is inherent in the nature of things and can never be surpassed by improved technique or increased skill on the part of the observer. For objects and systems governed by quantum mechanics, there is no way to observe them without fundamentally changing them. It has nothing to do with the measurement equipment, it has nothing to do with the conscious mind interpreting the results, it is the information extraction itself that is the observation. If a quantum system is subjected to conditions that allow information regarding its state to be unveiled, it has been subjected to an observation." Now let's apply this knowledge to the quantum rock. The quantum rock travels only in darkness, when you avert the flashlight or when you turn it off completely. The Nomai theorized that the rock was allowed to travel once it was no longer observed by a conscious being, which would explain the need for darkness. But as we now know, this is not the true reason why it has to be dark. As a light beam is aimed towards the quantum rock, it stays in place. This is due to the quantum Zeno Effect that prevents it from traveling while it is being observed. And in this case, once a photon is reflected off of the rock's location has been determined. According to how we define observation for quantum systems, the quantum rock has been observed. Once you turn off the lights, the conditions that the quantum rock is subjected to no longer allows for any information regarding its location to be unveiled. It can now move freely again. As you play around with the quantum rock, you might come across a phenomenon that seemingly negates the theory presented in this analysis, and further supports the Nomai theory. So you might have experienced the little scout in its bright glory disappearing with the quantum rock as no one is looking. That does not exactly seem to align with the theory that the quantum rock needs to be in complete darkness to travel. You may also have noticed quantum rocks disappearing in starlight, and your flashlight reflecting on the cave walls should also supply the quantum rock with at least some light. Well, to explain that, we will have to take a closer look at how the Zeno effect actually operates. We can no longer view it as a binary operation. What is actually happening is that the time evolution of the quantum phenomena is slowed down as the system is being observed. So in the case with the quantum rock, we can model it in the following way. The probability function that determines where the quantum rock will end up resets every time it is being observed. When the flashlight is aimed straight at the rock, it is being constantly bombarded with photons. and each photon hitting the rock corresponds to an observation. So the probability function resets very frequently as it is exposed to a lot of light and barely has any time to change at all, making it very unlikely that it will travel to a different location. In a dimmer environment, the probability function has time to settle between photons hitting it, making it more likely to travel to a different location. Now, for Hearthian-made equipment, such as the Little Scout, one would need to know the technology behind it to draw any legitimate conclusions. But let's say it's using some type of LED technology with a pulse width modulating dimmer function, leaving it off for short periods of time to get the desired light intensity. These off periods would be too short for us to see, but might be long enough for the quantum rock's probability function to settle, which would explain why the Little Scout does not prevent the quantum rock from traveling. While the flashlight might use a more traditional incandescent technology, emitting a more constant stream of photons, resetting the quantum rock's probability function more frequently, keeping it in place more efficiently. Now, if you think objects traveling between different locations when no one is looking is weird, I'm going to leave you with a bit of quantum knowledge that might be even weirder. According to our understanding of superposition of quantum particles, as the light goes out, the quantum rock does not actually travel to any other location. As long as the lights are out, the quantum rock is in all locations simultaneously.